All right, so 5.7 is on proving trig identities, which probably means nothing to you right now, okay? I'm gonna show you other identities that you guys proved in the last chapter. So this is the homework key from the last unit we did on rational functions. One of the sections was on proving identities. An identity, in the context we saw it, was just that one thing equals something else. That's it. You're just saying two things are the same, they're identical. And then in these problems, it was, are they an identity? And if they are, state the domain. So like on this one, to show that this is an identity, which it ended up being, but you had to figure it out, your goal was to take this and rewrite it, factor, simplify, until it looked like the other side. Once we did that, we could say, yes, this is an identity because these two things are equal, as long as W doesn't equal -2 or 1. Does that make sense? In trig, it's the same exact thing. So in trig, proving trig identities is proving, like, well, this is an identity. The tangent of x is the same as sine of x divided by cosine of x. That's an identity. I'm saying one thing equals the other. So proving trig identities is going to be rewriting one side, make it look like the other, to show that they are the same. Okay, so keep that in mind. You've done it before. All right, so just to recap, an identity, so we did this last class, is an equation that is true. It's an equation that's true. One side equals the other side. For all values that both sides are defined for. So that's why we state domain restrictions. So starting off with an identity that is important for us to remember is that tangent is the same as sine divided by cosine. When we state identities involving fractions, it's important to state the domain restrictions. To state the domain restrictions, we're going to need to remember when the cosine of x equals 0, because I can't divide by 0. So here's our handy dandy unit circle. We're going to put our 5 key points. I'm hoping by now you're doing this in your sleep, just imagining the 5 key points on the unit circle. Yeah. What? Pi halves is where cosine equals 0? Good. Okay, so I'm going to take the time to put that all on here. Yeah, so were you just visualizing it? Good. So this is 1, 0, 0, 1, -1, 0, 0, -1. And I'm specifically wanting to know for this example, tangent of x, where it's not defined, which would be when cosine of x is 0. So am I thinking x values or y values when I look at my key points? If I'm looking for when the cosine equals 0. X values. So here and here. So my domain restrictions are pi halves, 3 pi halves, 5 pi halves, 7 pi halves, right? So basically pi halves plus or minus any multiple of pi after. Because if you go to your first restriction, pi halves, how much farther until the next restriction? So think about like how many radians from here to here, that's pi. So starting at pi halves, every multiple of pi before or after that, you have this discontinuity. So x cannot be pi halves plus any multiple of pi. So I'll do plus pi n. These are all, these all consider, don't consider, memorize, learn, understand, and know. All of these identities are really important that you guys are going to be relying on as we prove other trig identities. So these are kind of like the tools. These identities are going to be our tools for proving more complicated trig identities. All right, secant of x equals 1 over cosine of x. This is an identity. This is true. That's the definition of secant. It's 1 divided by cosine. What are the domain restrictions on that one? It's exactly the same because cosine's in the denominator and it equals 0 when cosine equals, or when theta equals pi halves or any multiple of that. Okay, cosecant. We know cosecant to be 1 divided by sine of x. That is true. That's an identity that we're going to be relying on. When is that not defined? Where are problems for that? Zero, 1 pi, 2 pi, 3 pi, basically any multiple of pi. So that's just going to be pi n. So cosine in the denominator, what we had to avoid pi halves plus any multiple of pi. This one is just any multiple of pi. And then cotangent, so if tangent is sine over cosine, cotangent is the reciprocal, cosine over sine. And it's okay if you guys need to refer back up to these, especially today, but eventually you guys should be able to not, move away from referencing these identities. All right, so my restrictions on this are what? Any multiple of pi, just like the other one. We're really not concerned about the numerator, just that denominator sine of x, which is not defined for any multiple of pi. All right, so far so good? All right, so how can we show that an equation is not an identity? So here's an example. This is not an identity. We can expect that because we're talking about how to show it. All you need to prove that something is not true is one counterexample. And this goes for like even just logic statements like in our world. Like for me to say like all women, blah, 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 you could be like, actually, there is this one woman I know who doesn't do that. So that is not true. You know what I mean? So you can disprove a statement by giving one counterexample. And it's the same thing in mathematics. So if I wanted to look to check to see if this was an identity, all I would have to do is graph both sides. Does this one have the same exact graph as that? So that's what you guys would do if I asked you to. I'm not going to ask you to prove anything that's not true, but if I ask you to check and see if something is an identity, make sure you're in radians if you're going to be graphing trig. All right, so cosine of x plus sine of x quantity squared. Again, if this is an identity, then I'm going to graph one. Wait a second. Yep, square. On one y equals, the second one on the other y equals. You guys should know enough about math to tell me if this is true. Look what's happening. Cosine plus sine quantity squared. Is that the same as just squaring the individual pieces? Like if I said square, you don't need to write this down. X minus 2 squared. Is that x squared minus 4? Is that the same as x minus 4? X squared minus 2x minus 2x. This is not right. This is the most common mistake that I get so tired of seeing. That's not true. So the logic holds here. You can't just square both things inside of a parenthesis and have it be true. So we'll look at the graphs. I should expect different graphs. So here's the first one, cosine of x plus sine of x quantity squared. And then here comes the second one, cosine squared plus sine squared. That's interesting. Oh, it was up to 40. No wonder. Yeah, I did zoom 6. Here's cosine of x plus sine of x quantity squared. And then here's cosine squared plus sine squared. What? That's just a horizontal line. What does cosine squared plus sine squared equal? This was on your homework. The Pythagorean identity. It equals 1. So that's not a surprise when we really think about it. Oh, it's just a horizontal line at 1. Okay, those are not equal. All I need to prove it is provide you with one counterexample. That's it. I could say, look, these are not equal. For example, consider the x value. So you just need to find an x value where they don't have the same output. For example, like the value of 1. Those do not intersect when x equals 1. So all you would have to say is, counterexample, x equals 1. Done. I proved it to you. Those are not the same. All right. So I'm going to skip the next one and move on here to example 3 before we actually start proving identities. when you're proving identities, it is important to state the domain restrictions, and that's why we started off with those identities at the top. We always write the domain restrictions instead of the full domain. And anytime you are simplifying a trig equation or proving an identity, the goal, since basically every single one of these identities up here, tangent, secant, cosecant, cotangent, I can rewrite every single one of those in terms of sine and cosine. Like that's that's like our building block of proving trig identities, because we can write them all in terms of sine and cosine. So when you're looking at something like this, and we're proving to see if this really equals this, to show that, I would start breaking it down in terms of sine and cosine. And then when everything's in terms of that, then you can very easily, like we did up here, state the domain restrictions, okay? So tangent squared, how can I rewrite that in terms of sine and cosine? Squared, yeah. So it would be, or you can think of it as, instead of thinking it as this whole thing squared, you could just think of it as sine squared divided by cosine squared. Also, I get questions on this, like some people get confused by this tangent squared and then the x. That's just how we talk about trig functions to a power, because it can get confusing. I'll show you up here. Because if I wrote it like this, you're like, what, am I squaring x or am I squaring the tangent of x? And that's why we have tangent squared of x, because then you know you're squaring the tangent function, not just the x value. Does that make sense? Cool. Okay, so instead of tangent squared, I can write sine squared of x over cosine squared of x minus cotangent squared. What can I write instead of cotangent? No, cotangent, if tangent is sine over cosine, then it's cosine, then cotangent is cosine squared or cosine. So cosine squared of x divided by sine squared of x equals secant squared. Think about what secant is in terms of sine or cosine. Secant is the reciprocal of cosine. So secant squared is actually 1 over cosine squared of x. And cosecant squared, 1 over sine of x. So all I've done right now, we haven't proven anything. All I've done is just rewritten everything in this identity in terms of sine and cosine. And the reason I'm doing that is because now I can much more easily state the domain restrictions, because domain restrictions, just like in the chapter with rational functions, I'm just looking at those denominators. Here, sine of x and cosine of x can't be 0. So if we look back at our 5 points up here, that means not only can, it can't be pi halves plus any multiple of that, it can't be pi either. So it's literally combining all of these, right? So it can't be any multiple of not just pi, it can't be any multiple of pi over 2. So combining the restrictions for both sine and cosine, x cannot be pi halves or 1 pi halves or 2 pi halves or 3 pi halves or 4. So n pi n over 2. No multiple of pi halves. Does that make sense? Yeah, so the restrictions on cosine. So I'm looking for restrictions. Cosine of x cannot equal 0 because cosine is in the denominator. So then I would go back up here and it can't be pi halves, 3 pi halves. So it can't be pi halves or any multiple of pi after that. So that's basically these first 2 domain restrictions we started off with. But there are also fractions with sine in my denominator, which means I need to apply the restrictions we found up here, which was that theta or x can't be any multiple of pi, where sine equals 0. So because I have sine and cosine in the denominator of this equation, I'm basically combining all of those restrictions. So X can't be any of these 5 key points. X cannot be pi halves or 3 pi halves or 2 pi or any multiple of pi over 2, since this is kind of like scaled out by pi over 2. So that's why it's pi n over 2, any multiple of pi halves. Let's look at this next one. So cosecant, again, I'm not going to prove this. We will prove these eventually here in a little bit, but we're just focusing on identifying domain restrictions. So again, if you're looking at an identity and you're stating restrictions or actually trying to prove the identity, your goal is to rewrite it in terms of sines and cosines, because that's going to help you manipulate it to your advantage and simplify it to make it look like the other side. So cosecant of x, how could I rewrite that? One over sine of x minus sine of x equals cosine of x. So I'm leaving the cosines and sines. I'm rewriting everything else. How would I rewrite cotangent? Cosine over sine. Okay. So all I've done is just rewritten cosecant and cotangent in terms of sines and cosines. My domain restrictions on this are just coming from the denominators when sine of x equals 0. So my restrictions here, I'm only focusing on when sine of x equals 0, which is my y values. So that would be 0, pi, 2 pi, 3 pi, 4 pi, 5. So multiples of pi. So x cannot equal multiples of pi. Cool. All right, how do we prove identities? 3 basic techniques. They all look and feel the same. And I'm not going to focus on like the 3 different techniques very closely. You're going to find that this middle technique is probably, actually between techniques 2 and 3, probably the ones you end up doing. So the goal, just like we did with these, when I was proving these identities, what I did was take one side and rewrite it as much as I can to look like the other side. That's the first technique. Focus on one side, rewrite it to look like the other. So rewrite one side only using definitions, other known identities until it looks like the other side. The other technique would be rewriting both sides at the same time until they end up equaling the same thing somewhere in the middle. And that's the one I like because it's just like seems faster. Rewrite both sides independently. And I'm going to show you each of these techniques. And then rewriting both sides would be, just changing both sides using identities, and eventually somewhere in the middle, they're going to equal the same thing. Or transform the entire equation, the whole equation. And this one feels more like you're solving an equation. But eventually, again, you're going to end up with another identity along the way by using reversible steps. So that's reversible steps. That's how we solve equations. Like I'm going to multiply both sides of the equation by something, and then you can see that they're equal. So we'll look at all of these. Don't worry about like the names of them or anything once you have it down. Sorry that screen looks so blue. It's kind of annoying. All right. Okay, so we're going to prove an identity 3 times. Yay. All right, here's what we're trying to prove, that the tangent of x plus the cotangent of x equals the secant of x times the cosecant of x. Method 1, rewrite one side only. All right, when we typically prove trig identities, they're not proved until they're not proven until they're proven, right? So I tend to avoid writing the equal sign until I've proven that they're equal. So instead, what I typically do is just draw a vertical line and I manipulate one side on the left and the other side on the right. Give yourself some room. I put my line a little bit farther to the right of the equal sign because we will need some space. Okay, so I'm going to just focus on rewriting one side. So when I start rewriting, again, think in terms of sines and cosines. So instead of tangent of x, my first thing is going to be rewrite tangent as what? That's right, sine of x over cosine of x. plus cotangent of x, which is cosine of x over sine of x. And my goal is to make this left-hand side turn into secant of x times cosecant of x. I'm not there yet. The fact that I even have a plus sign, that's the next thing I want to change. And this chapter is intentionally, we're doing this intentionally after the last one, which is simplifying rational expressions. I need a common denominator. So I'm going to write all of this as a single denominator. What's the common denominator? Cosine times sine. Yeah, so this first function, I want to have a denominator of cosine times sine. So what do I multiply top and bottom by? Sine of x. So times sine of x here. On the right-hand side, or cosine of x over sine, what do I need to multiply that by? Cosine over cosine. Okay, so it looks like we're overcomplicating it, but that's going to help us because now I have a single denominator of cosine of x, sine of x. Are you guys with me still? The sine of x times sine of x, sine squared, plus cosine of x times cosine of x, cosine squared of x. Okay, now what? I don't feel like I'm close at all to secant times cosecant. You haven't trained yourself to identify this yet, but anytime you see sine squared of x plus cosine squared of x is a big deal. Why? The Pythagorean identity, it equals 1. That's huge. That's going to save you. That's going to be a shortcut in a lot of these. So I'm just going to put that up here because you will come to love this identity. It's going to be very useful. The Pythagorean identity. So this is literally the same thing as 1 over cosine of x times sine of x. Could I split that into 2 fractions? Like 1 over cosine of x times 1 over sine of x? You hate me or you love me?
I said I hate it here.
Oh, okay. Or do you love it?
I absolutely love it.
Well, yeah, this should be exciting because what's 1 over cosine of x? Secant. That's, oh my goodness. See, I knew you'd like it. Look, we just showed that this side equaled that side. Just by little steps using our knowledge. Does that make sense? Let's do the same exact problem, but I'm going to do my favorite method, which is technique 2, rewrite both sides together, and then they'll meet in the middle. So I'm going to start in the same way. The first step, always, rewrite everything in terms of sines and cosines, right? So instead of tangent of x, I'm writing sine of x over cosine of x. Instead of cotangent of x, cosine of x over sine of x equals, okay, here's where I draw my bar because I just want to, before I say they're equal, I just need to make sure. All right, secant of x. What can I write there? 1 over cosine times cosecant, which is 1 over sine. So all we're doing is using those basic definitions that we know for our main trig functions, right? Turning them all into sines and cosines. From here, and you guys are going to pick up on this too, this pattern of if I have 2 fractions being added or subtracted on one side, you're almost always going to write those as a single fraction. So that's where we need that skill of finding the common denominator, multiplying both fractions individually. So same thing, just like we did over here. So I want the common denominator. It's the product of the cosine function times sine function. So I'm multiplying my first one by sine of x over sine of x. And my second one by cosine over cosine. And that results in a single fraction with the denominator cosine of x, sine of x. Our numerator, again, sine of x times sine of x is sine squared plus cosine squared. On the right-hand side, anything I can do to the right-hand side to simplify? We could write it as one fraction. Yeah, I mean, the numerator is multiplied to 1, denominator is cosine of x, sine of x. There's not much else I can do on the right-hand side, but what can I do on the left-hand side? Simplify. Sine squared of x plus cosine squared of x is 1. Oh my gosh, look. Oh my gosh, and then we're done. So I didn't actually go the full process of making the left-hand side look like secant of x times the cosecant of x, but I slowly changed that one up a little bit until I get to a point where both of my sides have the same expression now. So this is why I like this one the best, because it just kind of shortcuts it a little bit. The last strategy is manipulating both sides entirely. I actually will walk through this one with you. The first step is the same, okay? I know you're tired of it. Rewrite everything in terms of sine and cosine. We're proving the same identity, by the way, just to demonstrate all of our options. Okay, so cotangent of x is cosine over sine. Secant, cosine, cosecant 1 over sine. So this last strategy is to manipulate both sides by applying reversible steps, which is like multiply both sides of the equation by this, subtract both sides of the equation by this until they equal the same. Because I didn't do that up here. I was individually manipulating the left, individually manipulating the right, and then they ended up being equal. This one, I'm going to actually multiply both sides of the equation by something. So in this case, imagine if I was solving an equation with denominators. Do you remember our strategy for that was multiply both sides by the common denominator? So let's watch what happens when we multiply both sides by the common denominator, which is, that's right, cosine of x, sine of x. Okay. Hang with me. When I take cosine x times sine of x and multiply it by my first fraction, what happens to my denominator? It's gone. What remains? Sine times sine, right? When I multiply it by the second fraction, what cancels? And what's left? Cosine times cosine. On the right-hand side, when I multiply 1 over cosine times 1 over sine by cosine times sine, what's left? And now what do we have? An identity. You're done. So if you, like this one, you have to be a little more clever in recognizing those identities. But after one step, boom, that's true. We're done. So these are the 3 methods, and they're all like kind of the same, but not the same. You know what I mean? And the hard part about this is, well, there's good news. The good news is if I say prove an identity, I'm never going to ask you to prove something that's not true. I'm not trying to trick you. So you can go into it knowing this is true. I just have to find the path to make it look like they're true. So let's practice a couple before we leave. All right, so on this whole next page, it's this one identity we're being asked to prove using all 3 techniques. We are not going to use all 3 techniques. Instead, we're going to use my favorite, technique 2. I like manipulating both of them at the same time. Okay. All right, rewrite both sides independently. I want to prove that 1 plus sine quantity squared whoops, 1 plus sine quantity squared equals 2 times 1 plus sine minus cosine squared. Okay, where is there a better one to prove? Let me see if there's not another favorite that I have. No, we'll do this one. All right, how can I change? So this one's tricky. They're all ready in terms of sine and cosine. So what can I do to the left-hand side? 1 plus sine quantity squared. Simplify? How do I do that? I wouldn't call it simplifying. Expand it. We've got a quantity squared. Literally the only thing we could do is square it. So I'm just rewriting it as 1 plus sine squared times 1 plus sine squared. What can I do on the right-hand side? Do the same thing. This 2, distribute it. 2 times 1 plus 2 times sine theta minus cosine squared theta. Okay. It's kind of like, I don't know how to move, so I'm just gonna do what I can, just one step at a time. So on the left-hand side for my next step, I'm actually gonna multiply that out. So 1 times 1, 1 times sine theta, just sine, plus sine theta times 1. So I have 2 sine thetas. Yeah, so sine theta plus sine theta is what's gonna result there. So that's 2 sine thetas, which is a good sign because look, on the other side, I also have 2 sine theta. Okay, and then my last one is sine squared theta. All right, so right now I have only sines on the left, and I have this random cosine squared on the right, which bothers me because there's no cosine squared over here. What are we gonna do about that? What's the Pythagorean identity?
I choose sine squared plus cosine squared equals 1.
What do you think I'm gonna do? Oh my gosh, you just thought of something I hadn't thought of.
Really?
Yes.
Are you being for real right now?
Yes, I'm being for real. Could we just add cosine squared to both sides? Yes, we totally could. I like that. I'll show you what I was going to do after. Because once I do that, I'm left with 1 plus 2 sine theta.
Oh, wait.
No, you're right. Plus sine squared plus cosine. So what can I write?
1.
And on this is gone, and I have 2 plus 2 sine theta. What do I have on the left? 1 plus 2 sine theta plus 1, which is 2 plus 2 sine theta. You thought of a different way. That's what's kind of cool about these problems is because like when I'm grading a test over this stuff, for example, my answer key wouldn't have looked like that, but this makes perfect sense. Like this is a logical way of proving it. What I was gonna do, so when I saw that cosine squared, I went back to this and thought I can solve for cosine squared and replace it with 1 minus sine squared of theta. So I'll show you what happened there. I would have had, I'll redo it, 2 plus 2 sine theta minus 1 minus sine squared theta, which would have been minus 1 plus sine squared theta. So 2 plus sine minus 1. What am I missing here? That's it. Yeah. Plus sine squared. So you would have, then you have the 2 minus 1. So I would have ended up with 1 plus 2 sine theta plus sine squared theta, which is the same as where I was when you saw Ellie, that I could just add. So there's different paths. That's a good thing and a bad thing because it's a little open-ended. The good thing though is that you know these are, they should work out. It's just you kind of like finding the way to do it. All right, before we go, I know we only have a couple minutes. Flip on over to example 8. We're gonna derive 2 more Pythagorean identities from our original Pythagorean identity. And these are gonna be more tools that you can use. And on your homework, like the first problem is like state the 3 Pythagorean identities. This is where the other 2 are coming from. The first one is exactly what you see, sine squared of x plus cosine squared of x equals 1. We're gonna derive another identity by dividing every single thing in here by sine of x, by sine squared of x. So I can do that. If I divide everything by the same thing, it's still equivalent on both sides. What's sine squared of x divided by sine squared of x? What's another way of writing cosine squared divided by sine squared? Cotangent squared. And what is 1 divided by sine squared? Cosecant. This is another Pythagorean identity. 1 plus cotangent squared is the same thing as cosecant squared. And then we could do the same thing, start with our original and divide everything by cosine squared. So earlier I just divided by sine squared, now we can do cosine. And we'll end up with our another version of the Pythagorean identity. So sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. So tangent squared plus 1 is 1 over cosine squared, which is secant squared of x. So this seems like a little like, okay, this doesn't really, okay, just another confusing thing for me to remember. It's not meant to be, it's meant to be a tool. So if you take the cotangent squared and add 1, you have cosecant squared. If you take tangent squared and add 1, you have secant squared. So these are other forms of the Pythagorean identities. Just as useful as our original. Okay. All right, so that gets us through this. Your homework for Monday, I want you to do that 5-7 worksheet, okay? And we will stop and go over questions. We're gonna actually just be reviewing Monday, kind of all of this. So we can address the transformations questions, we can address